Aloha, my name is Chong Ho Alex Yu. I am a professor of data science and artificial intelligence in Hawaii. In this video, I would like to discuss a potential paradigm shift in artificial intelligence, the Language Processing Unit, LPU. While Google's Tensor Processing Unit, TPU, has been widely recognized as a formidable challenger to NVIDIA GPU, another potential game changer, namely, the LPU, is now emerging on the horizon. In December 2025, NVIDIA acquired assets from Grok, a 9-year-old startup, for about $20 billion. Under this non-exclusive agreement, NVIDIA gained access to Grok's language processing unit technology, an architecture designed not to train ever larger models faster, but to run them more predictably, efficiently, and economically. For people accustomed to hearing that more floating point operations per second, flops, is always better, the rise of LPUs invites a rethink of what performance actually means in the age of large language models. To understand why LPUs matter, it is crucial to understand the brilliant mind behind LPU. Jonathan Ross, the inventor of the LPU and founder of Grok, does not fit the conventional mold of a semiconductor architect. Ross dropped out of high school because he found the traditional curriculum boring. Despite not having a high school diploma, he attended Hunter College in New York City before transferring to the current Institute of Mathematical Sciences at New York University, NYU. While at NYU, he studied honors mathematics and honors computer science. In his second year, he became the first undergraduate permitted to enroll in computer science courses restricted to PhD candidates, studying under experts like Yann LeCun. Ross did not graduate from university. He dropped out of NYU between 2008 and 2009 to pursue his career in high-tech companies, including Google. He jokingly remarked that he didn't want to cap his earning opportunity by graduating. In Google, almost improbably, he spearheaded the development of the first-generation Tensor Processing Unit, TPU, not as a flagship corporate initiative, but as a Google 20% project, the same category that once produced Gmail. Ross's team shocked the world by designing, validating, building, and deploying TPUs across Google's data centers in just 15 months. This background matters because Ross's career reflects a pattern: stepping outside institutional defaults and questioning assumptions others take for granted. The LPU is, in many ways, a hardware embodiment of that mindset. At its core, an LPU is a processor designed specifically for language inference. If GPUs are like Swiss Army knives, highly flexible tools that can do many things reasonably well, LPUs are more like a precision conveyor belt in a factory, optimized to move one kind of product from start to finish with maximum efficiency. An LPU executes a pre-compiled sequence of operations in a deterministic way. Once a model is compiled, the hardware knows exactly what will happen at every step, in every clock cycle. There is no dynamic scheduling, no guessing which thread will run next, and no surprises. This contrasts sharply with GPUs. Originally designed for graphics, GPUs excel at massive parallelism and flexibility. They thrive in training, experimentation, and research, where workloads change frequently and unpredictably. But that flexibility comes at a cost. When GPUs are used for inference, especially for large language models serving millions of users, the same request can take slightly different amounts of time depending on scheduling, contention, and memory access. Most of the time, this variance is invisible. At scale, however, it becomes expensive. Here is where the distinction between flops and determinism becomes crucial. Flops, floating point operations per second, are like a car's top speed. They tell you how fast the car can go under ideal conditions. Determinism, by contrast, is like knowing exactly how long your daily commute will take, every single day. For inference economics, the latter often matters more. If a system responds in 20 milliseconds one moment and 200 milliseconds the next, engineers must provision for the worst case. That means more hardware sitting idle just in case. Language processing units, by delivering predictable latency, allow operators to size systems precisely, reducing waste and lowering cost per query. In addition, traditional GPUs rely on HBM, high bandwidth memory, which is off-chip. Moving data between the memory and the compute core creates a memory wall that slows down sequential token generation. In contrast, the LPU uses hundreds of megabytes of on-chip SRAM as primary storage. This internal memory remediates the limitations of NVIDIA's GPUs. Simply put, it effectively eliminates the delay for weight fetching during inference. This is why NVIDIA's interest in LPU technology is strategically revealing. NVIDIA dominates the GPU market and has built an extraordinary ecosystem around it. Yet this success creates a risk described by the innovator's dilemma, a theory introduced by Clayton Christensen. The dilemma is not that incumbents fail to innovate, it is that they innovate in ways that protect existing products and customers, even when disruptive alternatives point to a different future. Kodak's obsession with the film market while failing to fully embracing digital photography is a good example. Graphical processing units are enormously successful, but they are not optimized for every phase of the AI lifecycle. Inference, especially large-scale, real-time inference, is becoming the dominant cost and performance bottleneck. By licensing LPU technology rather than attempting to replace GPUs internally, NVIDIA can explore a disruptive architectural path without undermining its own foundation. It is a classic example of hedging against the curse of innovator's dilemma. In addition, taking over a competitor would likely trigger intense antitrust scrutiny, but a non-exclusive agreement could give NVIDIA's access to the LPU technology without any legal hassle. Language processing units are not theoretical curiosities, they are already used in practice. In cloud environments, they power large-scale language model inference where predictable latency is essential. Think of customer service chatbots, code assistants, or enterprise knowledge systems that must respond instantly and reliably. In enterprise settings, such as finance, healthcare, or government, deterministic behavior simplifies compliance, auditing, and capacity planning. Even at the edge, LPUs show promise for applications like voice assistants or real-time translation, where responsiveness matters more than raw computational flexibility. Across these contexts, LPUs function as inference engines. Once the model is known, they run it efficiently, again and again. At the same time, LPUs are not universal solutions. They are not competitive for training models, which requires constant experimentation, dynamic graphs, and rapid iteration. The LPU is also ill-suited for early-stage research, where researchers want to tweak architectures daily. In these scenarios, GPUs, and increasingly other accelerators, remain indispensable. The LPU's strength is focus, but that focus also defines its limits. Seen this way, LPUs resemble specialized industrial machinery. A factory would never replace all its tools with a single assembly line, nor would it expect a conveyor belt to perform custom machining. Instead, different machines serve different roles. GPUs are the flexible workshops of AI. LPUs are the high-throughput production lines. One does not replace the other. The NVIDIA Grok agreement underscores this emerging division of labor. It suggests that the future of AI hardware will be heterogeneous, combining general-purpose accelerators with highly specialized ones. For data scientists and AI users, especially those outside engineering, the key insight is that performance is contextual. The fastest chip is not always the most valuable one. The most predictable system often wins in production. In conclusion, LPUs are real, deployed, and economically relevant today, but only for a specific slice of the AI stack: large-scale, low-latency inference. They are not replacements for GPUs, nor are they academic experiments. Instead, they represent a growing class of specialized accelerators tailored to the realities of running AI systems in the real world. As AI shifts from training models to serving them reliably at scale, the quiet rise of LPUs may prove to be one of the most consequential hardware developments of this decade. What do you think? Will the LPU become the next paradigm shift? Will inference, rather than training, define the next phase of AI and machine learning? If so, what other assumptions about performance might we need to rethink? If this video sparked your curiosity, feel free to comment with your thoughts, share it with colleagues, subscribe the channel, and like it to keep the conversation going. Thank you for watching. Mahalo.